Hello, and welcome back to the Cosmic Companion. This week we're joined by Dr. Laurent Montési of the Department of Geology at the University of Maryland. He recently developed new models of Venus revealing recent volcanic activity on our neighboring world. In this episode of Astronomy News with the Cosmic Companion, we also take an up-close look at our other planetary neighbor, Mars, as new findings uncover additional secrets of the red planet. We watch the launch of Mars 2020, NASA's latest mission to the red planet, and we also look at the potential for life under that ruddy surface. Soon after dawn on July 30th, NASA successfully launched Mars 2020 on its way to the red planet. This mission includes the Perseverance rover, equipped with multiple cameras and other instruments to study minerals within the Martian surface. The mission also brings the first helicopter to another planet, testing new technologies to explore other worlds of our solar system. Mars was a water-rich world in the distant past, although the surface of that planet is now completely arid. A mounting body of evidence suggests small deposits of salty water still exist just under the rusty surface. A new study from New York University Abu Dhabi suggests life forms may utilize radiation from galactic cosmic rays to aid these chemical reactions. The European ExoMars mission, due for launch in 2022, will become the first spacecraft to drill into the surface of Mars and could potentially find life hidden there. Today we're joined by Dr. Laurent Montési of the Department of Geology at the University of Maryland. His recent work suggests that some volcanoes on Venus may still be active today. This week on Astronomy News with the Cosmic Companion, we're happy to be joined by Dr. Laurent Montési. He is from the Department of Geology at the University of Maryland, and he's recently found out some interesting things about volcanoes on Venus. Welcome to the show, Dr. Welcome to the show, Dr.
Thank you. I'm happy to be there.
Thank you. So tell us, what did you find? What do we know about volcanoes on Venus?
Well, Venus, we know, is having a whole lot of volcanic activities over a long time. There are some entire regions that are covered with lava flows, and we have several volcanic mountains that have been identified for several decades. The question has always been how old really those mountains are, those individual volcanoes. And there's been a lot of work recently trying to look and search for evidence of very recent activity, current activity, which of course is very hard as Venus is covered with these clouds that we cannot really see very well through the surface. The best data from the Magellan mission is like 30 years old and plus, and so it's great data sets, very much like the image I see behind you. We can see volcanoes, we can see flows there. But at the end, it's also a static image, and we don't know if any of this feature is formed yesterday or if it was formed 100 million years ago. So we know there's been a lot of volcanic activity, but the question is always when? And if not today, why not?
Right.
So,
And so are you mainly using Magellan data, or are you encompassing data from radar surveys done on Earth or other missions?
So in terms of understanding Venus, the data we have is pretty much all from Magellan. At least for us, from a geological standpoint, it's all Magellan. And that was a radar. So the images we see, they are not quite the same as taking picture. They're really coming from bouncing a radar signal to the surface. And from there, we get an idea about what the surface is like. It is important to remember it's not the same as just taking a picture. There are places on Earth, in most volcanic places actually, where you can do similar type of, we can collect similar type of data. There have been some radar missions on Earth that have trying to see the topography and the radar reflectance on the surface. They're great in terms of providing us a background and a point of comparison to better understand what we see on Venus. But most of these missions do have a different objective. They're not all there. They're rarely there actually for the geology that we would need really for Venus. They can be there for land resource, they can be there for topography and things like this. So they're not exactly the same type of radar. The data is not exactly the same. There is another source of data that is very important for Venus actually is from radio telescopes. So for example, Arecibo has provided beautiful images and still does beautiful images of the planet, which very much complement what we see from Magellan. In our study, it's all based, well, most of it is actually from a numerical model of the interior. But then when we want to compare it to the surface observations, we use this Magellan data. The images and the shape, the relief that we can also see in those images comes from analyzing the radar signal as well. So it's all Magellan.
And what do we know so far about the geology there and how it differs from what we see on Earth?
So the geology has both a lot of similarities with the Earth and one major difference. So in terms of similarities, we see lava flows. We see faults, like, you know, what produces earthquakes on our planet. We see them in many, many places. So there's a lot of comparisons that can be done. Several people are thinking there may actually be evidence of sediment layer in some places. It's very brand new. I'm not sure this is completely published yet, but there are some questions about some evidence for that. The main difference is the way that it's organized at the scale of the planet. If you want to understand the Earth from a geological standpoint, very quickly you get to learn about plate tectonics. How the lithosphere of the Earth, now that's a more technical term, but it actually encompasses the crust and the very strong uppermost mantle. That together is what we call the lithosphere. That on the Earth is broken into the plates that are moving with respect to one another. So today, if you were to look at the deformation on the Earth today, you would see most of the plates does not actually move, does not change, but you have those blocks, and all the deformation is concentrating at the edges of them. If you see evidence of ancient faults in the interior, they're very old, they're very long gone. And these plate boundaries make a global network that separate these plates and allow them to move with respect to one another. And if we try to see the same thing on Venus, we don't see that. We have evidence of tectonic activity over some period of time, but it doesn't make this interconnected network that would enable large plates to move. And so that's something that's a very fundamental difference between the way that tectonics and volcanic activity actually on Venus is organized compared to the Earth. And so it's something we wish to understand.
That's fabulous. So of course that begs the question, why are we on Earth lucky enough or not to have plate tectonics, whereas Venus doesn't if our planets are roughly the same size?
So first off, we are lucky about it because it enables us to regulate our climate very likely and make it livable. Venus is just not a place you want to settle down at this point. So, and it may be because there is no plate tectonics. Essentially, the gases that are released by volcanic activity over time may not be able to be recycled, and then they accumulate and make a hell of an atmosphere. As to the why, well, that's kind of is the billion-dollar question, really. We don't really understand Well, actually, what we don't understand is why the Earth has plate tectonics. It is, from a theoretical standpoint, it is relatively easy to make a planet that does not have plate tectonics, because the outside of the planet essentially cools down by losing heat very efficiently to space, even with an atmosphere like Venus. And so that makes it has a very strong outer layer. The interior is much more mushy, hot, it's convecting, it's active in all likelihood, but the amount of stress that comes from the interior is not very large compared to the strength of the lithosphere. So it's actually very difficult to break the hard shell that is on the outside of the planet. So a place like Venus that doesn't have, I mean, it has some of those breaks locally, but again, not major plates that move for a long time. That's a little bit easier to understand. It just means the lithosphere is too strong compared to the forces coming from the interior and remain essentially intact. Or maybe it's broken in too many places, but it doesn't form like what we have on Earth, the plates and things like this. And how we do it on Earth is really something we don't understand. There needs to be strong interior, weak boundaries, so there needs to be a contrast on the strength. And there's a lot of ideas about what produces that contrast. Many of these ideas have to do with the presence of water in the Earth's lithosphere. But in details, we don't quite understand that just yet.
It's fascinating. So without plate tectonics, what is driving geological activity and these volcanoes on Venus?
So you still have a lot of heat in the interior of the planet. And so that heat still has to be lost in some ways. So the traditional, and one way that kind of came out of the Magellan data, again in the early 90s, one vision about the way that Venus loses its heat is that it would essentially accumulate it, the lithosphere would thicken, and at some point, it would essentially reset completely the cycle. It would essentially get rid of all the current lithosphere, make a new one completely. And at that moment, there will be a lot of heat being lost. What we see is that as that new lithosphere thickens, I mean, what has been thought is that as that new lithosphere thickens, it's getting harder and harder for magma to go through. So at the beginning, when it's very thin, it's still okay to go through. And so you would expect a lot of volcanic activity right after that event. And that activity would wane over time. And the time scale we think for this, the last event may have been something like about 500 million years ago. Mm-hmm. So that's not something very recent.
Right.
That's why the age of the volcanoes that we see there really becomes important. Are they from soon after that event, or are they much more recent? And what we've shown actually in our study is that in some places, we have evidence from the shape of an entire volcanic region that it is still possible today for the action of the interior, especially those things we call plume, essentially rising, kind of like a warm mantle balloon, if you will, to rise, produce melt. And this seems to be okay. It seems to be okay to associate that new melt and that activity with some structures called coronae. So a number of those coronae are evidence that even today, it's possible for the interior and internal activity to locally make it through that strong lithosphere and make the features we see at the surface.
And you're saying that these coronae are, if I'm correct, are unlike anything we find on Earth. Is that
well,
correct?
Ever since they've been observed, we've been trying to find an analog place on Earth. So there's been several ideas. It is nothing which is a direct analog.
Right. But they were found in clusters. What is, for the most part, what does that tell you?
So there's two kinds of clusters. Some of them are associated with essentially rifts, like what we have in the East African rift or the Rio Grande rift on Earth. Some of them are associated with these features, which means that maybe those rifts have helped the magma, the activity, reach the surface. In terms of the ones we found to be active, they seem to be forming a sort of annulus, a ring, through the southern hemisphere of Venus. We sometimes call it the Venusian ring of fire. There is a ring of fire on Earth, so it makes a nice little comparison, but let's be clear, the origin of this is very different. Because on Earth is where we have subduction that is part of the mantle that are going down, but on Venus, this active coronae must have a plume, a part of the mantle going up underneath it. So it seems like the mantle is some type of maybe a torus or something like an annulus in the mantle that is rising preferentially. We don't really know why that is. This is something very brand new. It would be nice to, first off, we need to confirm that this is the case, because the first evidence is not always, you know, the best one. We have to keep on checking for that. We have to always remember these stories. And then really try to understand why the convective pattern on the Earth, on Venus, would form either an entire ring that is upwelling or a lot more upwellings that are concentrated in an annular region. So we don't really know how it happens inside, but it probably tells us something about the way that this very deep convection is organized on Venus.
And yes, maybe totally left field, but when I first read the paper, my thoughts immediately went to hotspots on Earth. Could there be similarities between the two?
Absolutely.
Two events?
Absolutely. So on Earth, if we have a mantle plume in the mantle, what we expect to see at the surface is what we call a hotspot. So, and a hotspot is a region of the planet that has more heat coming out, usually associated with more volcanism. So Hawaii is always one that we like to point to. It's an island in the middle of the oceanic plate. It has no reason to being there except if there is one of those mantle plume or a hotspot underneath it. Yellowstone is potentially, probably another one of those. And there's a few other places like this on the Earth. Actually, pretty much the same kind of numbers as what we infer for Venus. There is a difference, though, and is that they don't tend to have really corona associated with them. That is that whole idea that you have, so the corona at the surface appears as a ring of tectonic and volcanic activity, and it's very large. The one we studied, each one of them is more than 300 kilometers in diameter. That's the distance from New York to Boston. So this is a huge structure. Okay, so Hawaii is much smaller than that. But the key there is that there's twofold. One is really plate tectonics, which tend to essentially smear the structure of a chain like what we see on Hawaii. And the other one is we have a lot of surface erosion that gets rid of some of the earlier structures. So for example, one of the analogs people might be thinking about, I mean, in western northwest US, there is the Columbia River basalt, which is actually a plateau of large volcanic outpouring. And it may or may not be related to Yellowstone, but essentially that could be the type of volcanic activity we would associate as a corona. Except that even though it's fairly young, it is completely cut by the Columbia River, for example. So even over the scale of just a few million years, erosion is getting rid of a lot of that structure. So that's the reason why the same type of hotspot activity may not form something that is a direct analog to the corona on Venus.
It's fascinating. And, you know, just speaking as someone who lives just a few hours south of the Grand Canyon, erosion can have quite an effect on the landscape.
Absolutely.
And so what sort of future studies would you like to see done on to learn more about Venusian volcanoes?
So in the very soon things, I mean, very close to what we just talked about, those Venusian coronae, there's still a lot we do not understand about them. When we tried to classify the activity, we looked at about 100 of them, 1/3 of which was, we could say, it's probably active. Another third, we could say it really looks inactive. And a third of it, we couldn't tell. And we couldn't tell because they were, maybe some of them were more complicated in terms of parts of it. They were elements of both active and inactive coronae. So we probably still need to refine our models to try to see how to explain those more complex structures. The giant one called Artemis, and now we're talking about an absurdly 2,000 kilometer wide things. That's crazy. It's very complex inside, and we want to understand more about that complexity to see if truly it's valid to count it just like the other coronae or not. So that's the interaction between coronae and rifts, variations in thickness of the lithosphere, maybe what would have been like if we really try to think 500 million years ago with likely a much thinner lithosphere, whether we would see a different appearance in some way. Those are questions we can start to pose to try to better understand the overall evolution of Venus, based again on the morphology of this coronae. The interior, why we have that ring of fire, that's something that should really be addressed. I'm a modeler, so to me, I'm thinking right away about mantle convection models and how we could try to force this structure to develop. But I mean, the other thing is, as we started with this conversation, the data is 30 years old. And we have better ways of doing it now. Now, don't get me wrong. I love the Magellan data. It's beautiful. There's a lot of information on it, and we're not done really analyzing it. But you could have a higher resolution radar today. With that, you would be able to see more details about the topography, what parts are up or down. In a lot of places, the coronae we could not classify was because the topography just wasn't clear enough. A few years ago, when we're talking probably like 20 years ago now, there was a mission to Mars called Mars Global Surveyor. And in there was for the first time a laser that was giving us reliable, high precision topography. And it completely changed what the type of studies we could do on Mars. So similar idea on Venus would really be a game changer about how we can understand its current situation as well as its evolution over half billion years. So there's plenty more models we can try to do the best we can with the Magellan data, but there has to be new data coming. That is really something important.
And of course, the Envision probe is scheduled for 2032. What do you hope to get out of that?
Yes. So Envision, for example, would have one of those much higher resolution radar as part of it. And I really hope that it does get to fly and does give us the information we need. As part of the planning for the mission, actually, the team was asking recently for suggestions about where to go, where to focus, because the problem about a very high resolution radar like what they have there is that you cannot cover the entire planet. So you have to select a few places to study in more details. And they were saying, where do we think there is the youngest or some of the most likely recent activity? I'm like, well, we did not set up finding that, but I can point to you 37 places I think are very good targets. So I hope that we're going to get to have a lot of conversations with the Envision team. It's a great mission, what they're trying to do, and it would really be helpful if it flew.
Great. Thank you very much. It was wonderful to have you on the show.
Thank you.
Thank you. And that was Dr. Laurent Montési of the Department of Geology at the University of Maryland. Next week on Astronomy News with the Cosmic Companion, we'll be joined by Dr. Dimitra Atri of the Center for Space Science at New York University, Abu Dhabi. His research seeks to use the Rosalind Franklin rover to find life hiding beneath the surface of Mars. Please stay safe, stay healthy, and keep your wonder alive. If you enjoyed this episode of The Cosmic Companion, please download and share the episode on YouTube, Facebook video, or any major podcast provider. For more details on space and astronomy news, please visit thecosmiccompanion.com or thecosmiccompanion.net.